This picture was then a young graduate student completing his PhD at University of Cambridge. He's an American, but studying number theory in Cambridge. Freeman Dyson is a legendary, eminent, and very senior physicist who started life learning number theory under G.H. Hardy at Cambridge. Freeman Dyson, well, he's an Englishman, right? In 1972, Montgomery was about to finish his PhD. He went to St. Louis to attend a conference in number theory, and then went to Michigan. He had been offered a job at the University of Michigan, so he went up there. According to him, he went there to buy a house. I don't know, a graduate student just finishing the degree could buy a house. He did. He said he paid the deposit, he paid money. Then he went to Princeton. Professor Showalter's home. As you can see, many of the stories that I'll talk about have something to do with Princeton. He went to Princeton for a mini meeting or something. And then this, at the Institute for Advanced Study, one afternoon during tea time, someone introduced him to Freeman Dyson. So Dyson said, the story that I read, now, so Montgomery, what have you been up to? So Montgomery said, well, you see, I've been looking at this distribution of Riemann zeta function, the non-trivial zeros of Riemann zeta function, and then I've been doing some computing, and I come up with the following observation. What he was looking at was actually, he was looking at the zeros of the zeta function along the critical line, the red line, and he was trying to compare the distances between two adjacent zeros. You know, you have the first zero, second zero, you compute the distance, you take the second and third zero, you take the distance, and so on and so forth. And then he was trying to understand whether there's any pattern that one could glean from looking at the zeros of the zeta function. And then Dyson said, oh, this is extraordinary. Have you noticed that what you have shown me is very close to the distribution of eigenvalues of random Hermitian matrix, which is a model for the energy levels of heavy nucleus, for example, uranium-238. Right. Now, this, of course, came as a surprise because Montgomery was doing something he thought was absolutely harmless, right? Number theory. Nothing to do with nuclear bomb. But here's Dyson, who was originally trained in number theory and then moved to physics. And actually, he did some brilliant work in nuclear physics. And so the two of them talked, and then Montgomery got the idea. After the meeting in Princeton, he went back to Cambridge to complete his degree, and actually came up with a formula, which I will not show, that would give an estimate on what is called the pair correlation. That means the distances between two adjacent, or the distance between two adjacent non-trivial zeros of the Riemann zeta function, right? And then this formula that he came up with, he did some computation himself, and that interestingly enough, they did show some correlation with suitably chosen eigenvalues of random Hermitian matrices. In fact, what happens was that very soon after this happened, this man called Andrew Odlyzko. Odlyzko is now professor of mathematics at University of Minnesota. But at that time, when this news broke out, he was working at AT&T. And when he heard about what Montgomery had discovered, he decided to do some real computation using machines at AT&T during downtime, right? When nobody's working at night, he would go and turn on the machine and did a computation. I don't know with how many computers to do parallel computing and so on and so forth. And he actually calculated all the way up to the what is that? The 10 billion zeros, no, 1 billion zeros, non-trivial zeros after the 10 to the 23rd non-trivial zero, and then to try to see in what way it could fit the Montgomery's formula. And here it is. So Montgomery came up with a formula to try to predict the distribution of the so-called pair correlation, adjacent non-trivial zeros on the critical line. And Orlisco then used a formula that would predict the distribution, and then also calculate the real distribution. It turned out to be, well, almost perfect match. So what you see here is that he calculated the distance given any two adjacent points, calculate the distance between them, and they seem all to congregate or concentrate at 1.0, meaning that on average the distance between two adjacent zeros is, well, about 1. High probability. So what does it tell us? It tells us that the non-trivial zeros of the zeta function, although they appear to be very random, they are not quite random. Although they are associated with what's called random Hermitian matrix. Oh, by the way, you know, a matrix is like a chessboard, right? On every square you put in a number. And in case you've forgotten. So, so the diagonal line is the one that goes from the leftmost top to the right down, on the right corner down below. And a matrix is Hermitian if that diagonal line serves as a mirror. So the thing that's above the diagonal is, and the things which are below the diagonal, they are reflections of one another. So if you have a complex, we're talking about a complex matrix now. So every box, there's an entry of a complex number. So if a complex number above the diagonal line is x plus iy, then its mirror image below the diagonal line will be x minus iy. Right. Now, classical linear algebra tells us that every matrix is associated with an equation, polynomial equation, and the roots of that polynomial equation that we call characteristic equation. Some people call it function. The roots are what we call eigenvalues. So, oh yeah, of course there are experts in the audience, so please bear with me if I say something that bore you. Okay, so so the match is almost perfect between the results predicted by the formula and actual computation. But really, the thing is that why did people, for example, in physics, come up with this idea of associating the energy levels of nucleus, heavy nucleus, for example, with the eigenvalues of random Hermitian matrix? This idea actually came from the physicist Eugene Wigner, another Princeton professor, in the 1950s. By the way, as an aside, as a graduate student, I actually attended a talk by Wigner. I think he was, I don't know, in his 60s or 70s. He went up to New Haven for once and gave a brilliant talk. It was a general talk, but everybody was really excited and inspired by his talk. He talked about the future of physics. Anyway, Wigner in the 1950s had already conceived the idea of understanding or analyzing the spectrum of heavy nucleus using the theory of random Hermitian matrices. But then Wigner, if you look back, was not really the first person to have thought that. Something like this already came out when Werner Heisenberg introduced the theory of quantum mechanics. In there, the notion of Hermitian matrix is fundamental. So this thing goes back to the origin of quantum mechanics, and it, well, continues. But the interesting thing, I guess, to the mathematician is why would something as pure as the Riemann zeta function, that has to do nothing with the physical world, so to speak, right? One would think that the distribution of the zeros of the zeta function would have anything to do with something in nuclear physics, right? Now, but this question, well, I think even today has not been answered. People are still wondering about that. But what I'm trying to emphasize at this particular point is the chance meeting that took place between Hugh Montgomery as a young man, graduate student, and senior, very established and eminent physicists like Freeman Dyson. If there was no such chance meeting, then it's not clear how, when would such a thing be discovered. But let me give another example of something like that. So the heading here is called seizing opportunities. In what way do people actually make discoveries? Research, of course, here we're talking about. I'll give another example of two people, very recent. This happened just a few years ago. Emmanuel Candes, who's a professor at California Institute of Technology. And as you can see, he's still very young, born 1973. Terence Tao, even younger, born 1975. This is a picture of Terence Tao. Terence Tao is professor of mathematics at the University of California in Los Angeles. He's considered the rock star of mathematics today. He won the Fields Medal, the most prestigious medal in mathematics, 3 years ago, in 2006. And he can do everything in mathematics. Anyway, so a few years back, Tao and Candes came up with a brilliant idea of what is called compressed sensing. And an example of how this method can be used is in what is called the one-pixel camera. Now, if you are familiar with the technology of current digital camera, what it does is that you have it's almost like a computer screen. You divide the screen into that many pixels, right? So if you have a screen of, let's say, 1024 times 2048, you come up with about 2 million pixels and so on and so forth. And then when you use the digital camera to take a picture, and each pixel will record some information. Right? If you take a picture of a landscape, for example, right, some pixels will take the part in the sky, and others will on tree, maybe a river, water, house, and so on and so forth. Then together, you get a picture. The only problem is that if you do that, a picture like that, let's say 8-bit per pixel, you are going to require something like the size of 2 megabytes to store all of that. Then later on, if you want to store it in a computer or you want to send it to people and so on and so forth, quite often, well, if you have, I don't know, 64 or 100 photographs like that, it will be too big. So then the idea of compression comes in. What the compression does in a typical application would be more or less to select the ones which are important. For example, you look at the average, cut the picture into many parts, many little squares, and each square, you don't take every information that's recorded in the pixel, but maybe just take the average, right? So average of this part of the sky is grayish, and that one is not. And then after that, if you do that, you certainly reduce the size significantly. But of course, the trade-off is that you lose information. Right. So that's something that, and quite often what is that when you take photographs like that, you don't actually, with good techniques, waveless. For example, you can actually get quite a bit of the information of the original picture and lose, well, just a little bit and not significant. The point is that you may take a picture that has the size of uses 2 megabyte storage to take it. But in the end, what you really use, you don't. For example, if the sky, that part of the sky is just plain white, for example, maybe just 1 pixel will take care of that part of the thing. You know, you record it to say this is white color on a gray scale, and then that will take care of everything. So what these two people did was to come up with this technique called compressed sensing, and would allow you to actually, in principle, just use 1 pixel to get a picture. And it's as good as what you would normally see, I guess, in the naked eye. And this, I understand, has been used and tested in some medical applications, MRI and so on. So it's a wonderful thing. But what I want to say is not so much, well, is okay about the discovery, but more about how the discoveries were made. I was told that because Terence Tao and Candace, Emmanuel Candace, both had daughters, was it, who went to kindergarten at the same place. So every day they drove the kids to the school while waiting for the kids to come out. They talked. So maybe one day they say, what about this compressed sensing? Oh yes, yeah, why not 1 pixel camera, right? So it is this chance encounter that I'm trying to say that is reminiscent of Montgomery and Dyson. And things like this, I'm sure many of you will have, who are seasoned researchers, will have had occasion, if you think back, that maybe there was a particular moment when you were talking to somebody, or when you met somebody, when something came up, completely unprepared, but somehow later on, some important results were achieved, right? Completely unanticipated, completely by surprise. And interestingly enough, this was one of the things that led to the discovery of this method. Let me give another example. This one is, of course, quite different. This one is, in a sense, you look at what has not been done. And if your mind is always ready for that, or been thinking about that, then you seize the opportunity and then you do it. This is the area of computer animation, and the person we are looking at, this picture, is the picture of Ron Facue of Stanford University computer graphics, computer science department, but he's in the computer graphics lab. And he started off as an applied mathematician, got his degree in UCLA, and after that did his postdoc at Caltech. Anyway, the last few years in computer animation, if you are familiar with some of the things they have seen, movies that use computer animation, a lot of the things that went into computer animation in movies that we see came from this guy and his group in that graphics lab. And what they did was they really exploited physics together in conjunction with what I would call continuous mathematics, and applied that with, of course, with brilliant computer algorithms, simulation, to come up with things that we see, for example, in movies. In movies like Poseidon, Star Wars, Ratatouille, and the latest WALL-E. And here is just a sample of what can be done. And what I want to emphasize is that until maybe the year 2000, 2001, there was some use, but maybe not as extensive as significant, of continuous mathematics in computer science. Computer science, I think when it first started, of course, everybody was excited and so on and so forth. There was a time when people were predicting that all you need is what we call discrete mathematics to do computer science, and that's it. Forget about, someone even suggested that we should just throw away calculus. No need, right? Just teach them combinatorics, and graph theory, that's good enough. And of course, I mean, some mathematicians were very happy about that, but some thought maybe this is the reality. But it's not true. So the point is that it was not until 2000 or 2001 that Fakub and his group used some very sophisticated continuous mathematics, right? And then actually invented some more, like level set method and so on and so forth, plus partial differential equation, Navier-Stokes equations, and so on and so forth, plus physics to come up with something like that. Here's an example of that. Is oil and water, pouring oil into water, and then after that, you have fire going down, and then the whole thing. Oops, have we got it? Let's see. I hope it's not hang. Oops.
Water and fire should not mix together.
Yes, yeah. Now I want to go to the next slide. Now it hangs. Okay. Now, so the thing is that it is almost like no man's territory. Nobody was looking at it. Maybe people were waiting for enough compute power to come. Maybe that was the reason. But for a long time, this thing was not. There was not enough attention that was paid to this. I think I need someone's help to go to the next slide. Yeah, it won't go to the next slide. Let's see. Do you need to reboot? Okay, good, thanks. Yeah. But of course, those were good stories, stories with good ending. But then we also have stories with not so nice endings, or at least sometimes we think so, or could have been better, I guess. This is what's called class field theory, and so-called and L functions. After Riemann introduced his zeta function, when he looked at the zeros of zeta function and so on and so forth, if you look at it more deeply, really you can actually extend the notion of zeta function to other mathematical structures, what we call number fields. I won't go deeply into that. And then on what's called number fields, you can actually also introduce a corresponding zeta function, and then look for solutions and so on and so forth. It's not just number fields, also function fields, and there's a vast generalization that of Riemann's idea that we know of today. Now, Emil Artin and Erich Haeckel were two mathematicians. The one on the right-hand side up there is Artin. The one on the lower left-hand side is the picture of Haeckel. Between the year 1920 to 1940, thereabouts, both were professors at the University of Hamburg. And surprisingly, both were working on more or less the same problem. But there's no record of them talking to each other. Okay? Each one came up with his own version of L function generalizing what Riemann had done. Artin published his first work on something on this L function in 1923. He continued to, I think, publish two more papers in 1930 and 1931. He left Hamburg in 1937, where to? Of course, Princeton, right? And Haeckel remained in Germany. Right? The interesting thing and surprising thing is that nobody seems to know whether they ever talked to each other. There was no joint paper, right? Maybe they didn't like each other, I don't know, right? And one wonders what number theory could have been if the two had talked to each other. But of course, there's another way of looking at it. Maybe because the two never talked to each other, each one used his own idea to develop the thing. And then because of that, in fact, number theory became richer. That's the positive way of looking at it. And this thing did not converge until, well, first of all, there was an student called Chong Tat, who later became professor at Harvard. And Chong Tat's thesis was the first step towards trying to synthesize these two approaches. But now these two things have all morphed into what is called the Lang-Lanz program. Robert Lang-Lanz is professor at the Institute for Advanced Study in Princeton. And the Lang-Lanz program is one of the major mathematical programs today. So this is an example of an opportunity that, was probably missed. But so something could have been better, but didn't quite happen. Here's another one. This concerns Freeman Dyson himself. And Freeman Dyson gave a lecture. Freeman Dyson gave a lecture in the year 1972 to the American Mathematical Society, where he talked about, among other things, his own experience in what he called missed opportunity. Ramanujan, as you will know, was a mathematical genius in a village in India somewhere. And although he was isolated, he had this great mathematical talent that came out with lots of calculations about numbers, prime numbers, natural numbers, and so on and so forth, and lots of formulas. And the Ramanujan tau function was one of those things that he had conceived and studied by some mathematicians. Right. So Dyson said that before he became a full-fledged physicist, he was a number theorist. So from time to time, even after he became a physicist, when he wanted relaxation, he would go back to mathematics and try to solve some problems. So here's the Ramanujan tau function. Just look at the formula on the right-hand side. The big pi there represents multiplication. So you have x in front and then multiply, right? 1 minus x to the power n, and then the whole thing raised to the power k, okay? And then if you do the multiplication, like if you have time that is interested, and then you do the summation and so on and so forth, you can actually express that as a summation of tau n and with x to the power n. Tau n is just a coefficient, so it's a coefficient of the term x to the power n. And what Ramanujan did was he was looking in particular at the case when k is 24. I'm not a number theorist, so I don't know why he was looking at 24 and not 25 or 23. Anyway, he's looking at 24. Now, Freeman Dyson, sorry, I want to come back to this. Look at this thing. And he discovered that for certain powers of k, like what we have here, 3, 5, 8, and 14, 15, 24, 26, and so on and so forth, he could come up with some very elegant formulas. In fact, in his lecture, he did show, in particular for n equal to 24, k equal to 24, there's a very elegant formula that would describe the coefficients tau n. And then he was looking at all the other cases of k where he did have elegant formulas, and he was wondering why. Why is that such a thing? Why these numbers would give you nice formulas but not other numbers, and so on and so forth. And he said the reason that he was baffled was because at the time he was looking at this, he was looking at it as a mathematician and not as a physicist. Namely, he said if he had put his physicist hat on, he would have noticed that these numbers are nothing but the dimension of finite dimensional simple Lie algebras. And as anyone who does particle physics would know, the Lie algebra